Alright, so good morning. Looking at, actually, I should say good afternoon or good evening, depending on when you're watching this. But what we're going to do today is we are going to start reviewing our right triangle trig from our geometry days. And so I'm also going to introduce some other trig ratios that are out there other than sine, cosine, and tangent. And I also want to kind of give you a little bit more background of why, our calculators do help us so much, and what does sine and cosine and tangent do. So, hopefully I'm able to answer those. Now, I want to take you back to geometry when we talked about special triangles. And special triangles are those 45, 45, 90 triangles and the 30, 60, 90 triangles. Now, of course, you can't see this whole thing, so let me just view. I'm going to do the whole page here. And these three examples here, you've got 45, 45, 90 triangles. Now, hopefully you can recall that the fact that these angles right here are congruent to each other, that tells us that this has to be an isosceles triangle. So if this length over here is 4, well, then this side here has to be 4. Same thing goes with all of these triangles right here. These two legs would both have to be 8. Now, using Pythagorean theorem, if I were to take 4 squared plus 4 squared and set that equal to c squared, we can figure out what our hypotenuse is going to be. And so 16 plus 16 is 32 equals c squared. And then I'm going to take the square root of 32, which would give us c. And that would simplify down to 4 square roots of 2. If I did the same thing with 8 and 8, so 8 squared plus 8 squared equals c squared. And then if I were to go ahead and solve that there, you're going to end up with 8 square roots of 2. So if you remember that shortcut, and really the reason why we're getting 8 square roots of 2 here is because, think about this, here you're taking 2 times 8 squared equals c squared. And this is, sorry, my computer here is, okay. And then when you go ahead and take the square root of everything, that square root of 8 squared, well, that's going to give us the 8, and you have to leave the square root of 2 underneath there. So just kind of a little shortcut for us. Well, what about if you know what the hypotenuse is, but you don't know what the two sides are? Well, here you could still use the Pythagorean theorem of x squared plus x squared equals 6 squared. So 2x squared would equal 36. And then we divide both sides by 2. So x squared is going to end up giving us 36 divided by 2. Why can I not think right now? 18. And then I take the square root of that, and I get x is equal to 3 square roots of 2. And then that gives us our two sides. Now, you might have remembered, though, a shortcut with special triangles, and especially 45, 45, 90 triangles. Go back to the whole page here. And that is, once again, that tells us here that our two legs of the right triangle have to be congruent to each other. And then your hypotenuse is one of those legs times the square root of 2. And that right there is just giving us that shortcut. Now, what about 30, 60, 90 triangles? So here I've got 3 examples. Again. And when you look at angles, again, back to your geometry days, your shortest leg is opposite of the smallest angle here. So 5 being the shortest leg, 60 would be, opposite of that would be longer, and the hypotenuse we know is going to be the longest side. Do you remember that your hypotenuse is always double what your shortest leg is, and your longest leg is the shortest leg times the square root of 3. So using that information, if the hypotenuse is 18, that means that our shortest leg would have to be 9, and the longest leg here would have to be 9 square roots of 3. Now, it's a little bit more challenging to work with 30, 60, 90 triangles and using Pythagorean theorem. It's easier if you are to work with the rules behind it. So here you've got your shortest leg, your hypotenuse is 2 times that, and then your longest leg is n times the square root of 3. Now, I didn't do that last example yet because I'm going to use this concept right here to be able to solve for that. Because I know that down here my longest leg is 12, so that has to equal n square roots of 3. And to solve the other two sides, really, if I know what n is, I can figure out what the other two sides are. So 12 equals n times the square root of 3. We are going to divide by the square root of 3. Now, one thing I'm going to let you know is that this chapter we are going to be dealing with a lot of radicals, and you are going to need to simplify those radicals, which means that I'm going to have to multiply the numerator and denominator by the square root of 3. And so I get 12 square roots of 3 divided by 3. And then 12 divided by 3, well, that's 4. So 4 square roots of 3 is equal to n. So that means that our shortest leg here would be 4 square roots of 3. Double that, and we get 8 square roots of 3 for our special triangle that's here. All right, so now, went over all that. Now to go back to those good old days of right triangle trig. And our SOHCAHTOA days. So right triangle trig, and you probably remember seeing this: sine, cosine, and tangent. And hopefully you remember that sine is your opposite over the hypotenuse, cosine is the adjacent over hypotenuse, and tangent is opposite over adjacent. Now I am using this symbol of theta right here to represent the angle, my reference angle. So the sine of theta, opposite of theta would be little a here. Opposite, or hypotenuse would be c, so a over c. Cosine, b over c. And tangent, a over b. Now, the thing that's unique about things is now when you start to look at using your calculator, if you remember back when we did geometry, when you did like something like the sine of 45 degrees or the cosine of 52 degrees, your calculator has some number to go with that. Well, that's because your calculator knows every single ratio that is created with triangles. When you're working with trigonometry, you are working with similar triangles, okay? So if I go back to these triangles right here, all 3 of these, and I hate how I don't have this all on the same screen. Sorry. Zoom out again. I should just stay in that mode. All right, so when we look at these triangles right here, these triangles are all similar triangles. They're not congruent, but they are similar because of angle-angle similarity. And when you look at them, notice that, they have a scale factor between the two of them, if you remember that from geometry too. So working with corresponding sides. So if I take the first 2 triangles here, 4 corresponds with 8, and then 4 square roots of 2 corresponds with 8 square roots of 2. Well, all of these right here end up with a ratio of 1/2, and that's your scale factor, okay? Well, what also happens then is that since all these triangles are similar to each other, there are ratios that are happening within the triangle. So I'm just going to, obviously you have 2 angles of 45 degrees right here, but let's just take these top angles of 45 degrees. If I were to take the opposite side and the adjacent side, so 4 over 4, which equals 1. If I were to take 8 over 8, that equals 1. If I take 3 square roots of 2 divided by 3 square roots of 2, I get 1. All of these have the same ratio, and what I'm just doing here is I am taking the opposite over the adjacent, which is the same thing as taking the tangent of 45 degrees. Now, if you were to take the tangent of 45 degrees and put it into your calculator, you are going to end up always getting 1. It doesn't matter what happens, because a 45 degree angle, the calculator automatically knows you're dealing with a 45, 45, 90 triangle. Your sine, your cosine, and your tangent right there are referring to working with right triangles, so it knows the other angle has to be 45. Now let me go to 30, 60, 90 triangles. Now when I look at these here and I take an angle, and let's go ahead, let's take the 30 degrees that's here. Okay, and this time I'm going to do the opposite side and the hypotenuse. So 5 over 10, 9 over 18, and I take 4 square roots of 3 over 8 square roots of 3. All of these right here end up having a ratio of 1/2. Now, if you take your calculator and you take the sine of 30 degrees, sine of 30 degrees is going to give you 0.5, and that's the same thing as having 1/2. Now, just real quick, in case you were not getting those values of 1 and 1/2, you might be in the wrong mode. So on your calculators, if you go to mode, what you want to do is you just want to make sure that you are in degree mode. So down here, if you just make sure that that black bar is on degree, hit enter if not, and then you can quit out of there. And so then I think I did the sine of 30 degrees. You should be getting the 0.5. All right, so, and that works all the time here. Now, if I were to just go back to our special triangle right here, and we were working with 30 degrees, and so we said that the sine of 30 degrees is always going to be 1/2. Sine is opposite over hypotenuse, so n divided by 2n, n's would cancel, and you'd get 1/2. If you were to take the cosine of 30 degrees, then you'd be taking the adjacent, which is n square roots of 3, divided by the hypotenuse, which is 2n. And here you end up with the square root of 3 over 2. Now you go to your calculator, and you take the cosine of 30 degrees, and I get this decimal. Well, take the square root of 3 and divide it by 2. Notice it's the exact same thing. It's just an irrational number that you're working with. If we were to take the tangent of 30 degrees, no matter what triangle you have, okay, tangent here would be opposite over adjacent. So n over n divided by the square root of 3. N's would cancel, so we get 1 over the square root of 3. Rationalize that denominator, so square root of 3, square root of 3. And we would get the square root of 3 over 3. So once again, I just take the tangent of 30 degrees, and that's the same thing as the square root of 3 divided by 3. Every single right triangle that's out there, okay, we know one of the angles is 90 degrees, the other two angles have to be complementary to each other. And all of the ratios then between its opposite, its adjacent, its hypotenuse are all going to have a specific ratio to work with. And that's the beauty behind using our calculators now. So when I take the sine of, say, 75 degrees, that number right there is whatever that ratio is going to be for a 90 degree or right triangle. Has a 75 degrees, it would be 75, 15 degrees and 90 degrees. And the ratio between its opposite side and its hypotenuse would be this decimal. And that's where all of this comes into play and where we have to use our calculators to do much of it. Okay? So, just kind of a quick little tidbit here. Remember your sine, cosine, and tangent. Here I have a right triangle, 3, 4, 5 triangle. I think I can go back into my normal display now. And just creating ratios. The sine of theta, here's where theta is. Opposite of that would be 4. Hypotenuse would be 5. So we get 4/5. Cosine would be the adjacent side, which is 3. Adjacent means next to. So next to theta, and your hypotenuse is 5. Now you might say, well, isn't 5 adjacent to theta? Yes, but 5 is the hypotenuse of the triangle. The side opposite of 90 degrees, that's always going to be your hypotenuse. Tangent, opposite over adjacent, so 4 over 3. Alright, so sometimes when you have triangles, you're not going to have perfectly nice values to work with. So you might have some square roots. Still simplifying them. Sine in this case here, so opposite over hypotenuse. So 5 over 5 square roots of 5. I do want you guys to simplify. Now these 5s, they're going to cancel, so I get 1 over square root of 5. And then rationalize your denominators. Multiply numerator and denominator. Sorry, my computer sounds like it's kicking into high mode here. Square root of 5. 5 times 5 is 25. Square root of 25 is 5. Cosine. Here we're going to take the adjacent side, so 10 divided by the hypotenuse, which is 5 square roots of 5. We could simplify this to 2 divided by the square root of 5. And then I rationalize my denominator. And I get 2 square roots of 5 divided by 5. Tangent, opposite over adjacent. So opposite of 5, adjacent is 10. My tangent is 1/2. Now there are another 3 ratios that go along with sine, cosine, tangent that we did not cover in geometry, and that is the reciprocal identities. Cosecant, secant, and cotangent. Okay? Reciprocal means you're flipping the fraction around, so 1 over the sine is referred to the cosecant. We abbreviate that CSC. And so since you're taking the reciprocal of sine, now it's hypotenuse over the opposite side. The reciprocal of cosine is the secant, which then is taking the hypotenuse over the adjacent side. And then the reciprocal of tangent is the cotangent, which is taking the adjacent over the hypotenuse. Over the opposite side. Now, one thing that you just have to be careful about here, and I always wish they changed this or like had these switched around, but the fact that this is sine, now sine starts with an S. Cosecant starts with a C. So be careful with those. And here cosine starts with a C and secant starts with an S. Cotangent, that one doesn't seem to get mixed up too much. But just kind of be aware of that. So now knowing that information, what we should be able to do is not only come up with 3 trig ratios, but actually come up with 6 trig ratios. So here I've got my 3, 4, 5 triangle once again. Sine is 4/5. So that means that the cosecant is going to be 5/4. Cosine is 3/5. That means the secant is 5/3. Tangent is 4/3. Cotangent would be 3/4. All you're doing is taking the reciprocal of those. Now what happens if I gave you only 1 trig ratio and you had to find the other 5 to go along with it? Here I'm telling you that sine of theta is 5/6. Now if you just draw yourself out a triangle, put an angle of theta, you know 2 of the 3 sides to this. Sine is opposite over hypotenuse, so opposite of my theta would be my 5. My hypotenuse would be 6. Now realize that this might not be your exact triangle, because this is going to be a simplified version of it, because these ratios are obviously in simplified form. Well, now think about how you're going to find the other side, and that's where our Pythagorean theorem comes into play. X squared plus 5 squared equals 6 squared. So if we take 6 squared, which is 36, and subtract 25, I get x squared is equal to 11. That means that my adjacent side right here is the square root of 11. So sine being 5/6, I know the cosecant would have to be 6/5. cosine would be the adjacent over the hypotenuse, so square root of 11 over 6. The secant would be 6 over the square root of 11. Rationalize that, and we get 6 square roots of 11 over 11. Tangent would be opposite over adjacent, so 5 over the square root of 11, which simplifies to 5 square roots of 11 over 11. Notice that I'm not really showing my work here because some of you are going to be able to see that and know how those are going to simplify, and that's perfectly fine. Cotangent, take the reciprocal of that. We've got the square root of 11 over 5. And so now you have the 6 exact trig ratios. Let's take a look at another one right here, giving you that cosine of theta is 7/9. Why don't you try to pause the video and try and see if you can come up with the other 5 trig ratios. All right, check them over, see how you did. For your opposite side, you should have gotten the square root of 32, which I can break that up into, because you're taking the square root of 32, so I'll break that up into the square root of 16 times the square root of 2, and that gives me 4 square roots of 2. So sine, 4 square roots of 2 over 9, cosecant 9 over 4 square roots of 2. So I rationalize my denominator. 9 square roots of 2. 2 times 2 is 4. Square root of 4 is 2. 2 times 4 gives us where that 8 is coming from. So that right there is section 4, being able to set up the different trig ratios for the right triangle.